Thanks. So first, I would like to thank Vedika and all organizers for inviting me to give the talk. So this, yeah, I enjoyed a lot of, learned a lot of new things during this conference. The topic I will talk about is kind of more on the fundamental side. Please feel free to stop me anytime, in case that's a bit abstract. Yeah, so the motivation, I will start with some motivation. So basically, I think this audience is very familiar with quantum information concepts like mutual information. And we like mutual information because it's characterizing correlation in a many-body system. And so if you have a many-body state, then you can look at different regions A and B. They need to have a Hilbert space that are independent, right? Hilbert space of HA times HB, and then you can look at their mutual information. So, but now this the question is whether there is something like this in space-time. And the reason why we ask that is, okay, so if I think about a relativistic system, there is a light cone, then you can draw you can draw regions like this, and if they are space-like separated, then you have a quantum state defined, right, along a line like this. And if they are time-like separated, I cannot talk about the quantum state of A and C. And if we don't think about relativistic system, the same thing happens in like a quantum circuit, right? So if you have a quantum circuit, then you also have a light cone. There is regions which are time-like separated and regions which are space-like separated. So then in these cases, there seems to be a fundamental difference. But on the other hand, if you think about doing experiments to the systems, like for example, the very beautiful experiments we heard in the earlier session today. If you think about doing any experiments, then I could measure spatial correlations in my experiments. I could also measure space-time correlations. What I need to do is to introduce some ancilla which couples to degree of freedom in A and coupled to degree of freedom in B, and then collect my data, and it may be quantum or maybe classical, and then measure their correlation. So I could do that for space-like separated regions. I can also do it for time-like separated regions. So it seems like there should be a description of correlation between these different time-like regions, which is similar to mutual information. And we would like that instead of just particular correlation functions, because that will give us a kind of unbiased measure of how much correlation there are between these regions, independent from what a particular measurement you do. So that's kind of the motivation of this work, that we want to generalize mutual information. And this is a work in progress in collaboration with Paolo Glorioso and Zhenbin Yang, both postdocs at Stanford. Paolo is here also. I hope he's here, so he can answer questions if I. Yeah, so there are several works related to this that I listed here, which are earlier works. Okay, so I think we don't need an overview of mutual information. It's given by this formula of von Neumann entropy, and if you consider a state of AB, two regions, then the mutual information has some nice properties. First of all, it measures how different the state is from the product state, right? The mutual information is zero if and only if the state is a product state. And one of the nice properties it has, which will relate to our discussion later, is it bounds correlation functions, as pointed out by this work. Any connected correlation function, when you divide by some norm, is bounded by mutual information. And as a trivial fact, of course, if you take n copies of a system, and then even if you jointly measure the n copies of A and n copies of B, the same bound will apply, right, after you divide by n. So we will also have some discussion like that later. And then there are some other properties of mutual information, which is, for example, it has a monotonicity. When you have a state of A and B, and then if you do some operations on B that's independent from A, then the mutual information can only go down. Right? If you independently do anything on A and B, which are like measurements or any quantum channel that couples the system to something else, then the mutual information can only go down. And as a special case of that means if you look at a mutual information of A with a region BC, and then you shrink the region size, when you go from BC to B, that mutual information can only go down. Right? So that's what gives us the strong subadditivity of entropy. Okay, so this is an important property because it tells us that this is an intrinsic measure of correlation. That if you don't introduce new correlation, there is no way to increase it. Now, for the generalization we want to discuss, there is an important relation between mutual information and relative entropy, which is where we are going to make this generalization. So, so we know, so mutual information is a relative entropy between two states, which are just your physical state and the factorized state rho A times rho B. If you take these two, the relative entropy is equal to mutual information, and actually this kind of monotonicity properties are all properties of relative entropy. And one thing we like there are different interpretations of relative entropy, but one interpretation we really like because it is very operational, physical, and allows us to make this generalization is the hypothesis testing, which means, okay, roughly speaking, the relative entropy measures how different are the two states, rho and sigma. So in what sense? In this, we can formulate this Gedanken experiment. Say there is a black box, which I tell you, okay, there could be a state sigma or rho. And then you say, I make a conjecture that is sigma. And then you do measurements, and I give you n copies of that state. And then you do n identical copies. They are either all sigma or they are all rho. Okay, and then you do measurements, and then if it's sigma, probably you just verify, oh, that's agreed with my understanding of sigma. But if it's actually rho, you made the wrong conjecture. You wouldn't say, okay, I do a measurement and say I must be wrong. Right? Because everything is probabilistic. Instead, what you will do is you do the measurement n time, you measure n copies of the state, and then you say, if it's sigma, the probability I see this output is exponentially small. That's how I say I probably was wrong. Right? My conjecture that is sigma was probably wrong. So that rate, that how fast you find out the difference between the two states is given by the relative entropy. Right? The probability that you think the probability you are right decays exponentially with n, and the rate that decays is relative entropy. Okay, so you can check that in a very simple example, right? If you have two states that are classical, just classical probabilities, then if you have a hypothesis, then you can compute after you measure, you throw the coin n times, what's the probability of seeing each input, right? Each output, sorry, and then you will see the output corresponds to the actual state is somewhere here in the tail of your distribution. And what is that probability? You can check that is given by this relative entropy formula. So yeah, that's just saying that you could formulate this relative entropy as in this kind of operational way. Is there any questions so far? Yeah.
Is this assuming you have like an optimal discriminator between the two states or something? Or
it's kind of when you say optimal discriminator, it sounds symmetric between rho and sigma. But the way relative entropy is not symmetric, and there is the fact that it's not symmetric is pretty essential, because like if you take a pure state and a maximally mixed state, then rho sigma relative entropy could be finite and S sigma rho could be infinite. And you can see it from this way you formulate it's like you make a conjecture. Sigma is your conjecture, and rho is the actual state. Okay, good. So now we are ready to make this space-time generalization. So once we formulate this into a hypothesis testing, then it's natural to think about the space-time generalization, which means you just put in your black box, instead of just putting that quantum state n times, you put the entire quantum system, which means you have a state and the time evolution, just your experimental system n times in this box. And then so this L is your quantum system, and I want 2n times for the reason you'll see immediately. So let's say I have 2n copies of that experimental system, and I'm evolving them so they have identical initial state and identical time evolution. And then there is a hidden variable, classical variable, which is just 1 bit, which could be 0 or 1. And what that controls is basically the generalization of that difference of rho AB and rho A cross rho B. What that does is if that variable is 0, then, okay, so I'm doing experiments here. This is my experimental ancilla. This is my apparatus in my experiments. Then you are allowed to do anything to your physical system, but only restricted to the space-time region A and B, which means let's say A happens at time 0 and B happens at time t, and let's say A is like the first qubit and the region is B is like maybe the second and third qubit, and then so I tell you, okay, you can do anything at time t equal to 0, you can do anything to the first qubit. And then you go away, and then later at time t, you can do anything to the qubits 2 and 3. That's the only restriction you have. Your system here, the apparatus could be arbitrarily large. It could be you can use a quantum computer, or you can do anything, but you are restricted to this 2 space-time region. Okay, and then your task is to distinguish the 2 cases. One case, the case 0 means like after I couple the system at time 0, I swapped in a fresh new copy. Maybe it's easier to look at the picture here. Case 0 is after I do the measurements at region A, I swap in a fresh copy and then do measurements in a separate n copies on region B. So by design, I'm not seeing any correlation between A and B. I'm just doing them on separate systems. And then case 1 is the more physical case, which is you measure something in A, you measure something in B, so generally you will see some correlation. So that's the analog of rho AB for case 1 and rho A cross rho B for case 0. And so that's the most general thing you could, like experimentally you do something like this. That's what you do, the case 1. And then you say, okay, I want to find out whether that state is actually correlated. So the precise way to formulate that is you could make a conjecture that is case 0, and then see whether you can find, like, then you do n copies of measurements and then say, okay, it's very unlikely that conjecture is correct. If there is correlation, I will find out that with this probability that's given by relative entropy. So now it's natural. So because of this relative entropy is related to this hypothesis testing, now it's natural to define our space-time mutual information as this relative entropy of the output state. So you are allowed to do anything here and anything here. The only condition is you access only that space-time region and that space-time region. And you don't know if case 0 or case 1, then you look at the output state of your ancilla, W, at the blue line, right? After you do the coupling, VA and VB. VA and VB are general unitaries. And then you look at the sigma W and look at the relative entropy of the state for case, the difference between your hypothesis, which is the factorized state, and then the other one is the actual state. So you look at that relative entropy and divide by n. And then there is a immediate simplification, which is this VB. This VB is because after you apply VB, you immediately take out the state of W and measure its relative entropy. So instead of looking at the relative entropy of the state of the output, you can just look at the relative entropy before you apply VB, but for B and W. Because relative entropy has this monotonicity. So if you look at that relative entropy, it can only be bigger than this. And you can show that it could be equal. So instead of saying I look at the output state and optimize with VA and VB, I could say I can just get rid of the optimization of VB and just look at the state at the red line of sigma, look at the state at BW at the red line, and then optimize with VA. So that will be the definition we will use. Like for generality, we allow you to access n copies of systems, right? You could, generally, you may be able to do some quantum experiments that you access n copies of the system at the same time rather than one by one. So generally, you have n copies of the system, and then you compare the case that's factorized and not factorized, and look at that optimized with the experiment you do. You tune the VA, and make optimization. So that's I think I want to pause here and see if there are questions, because this is the definition. Yeah.
System.
Sorry, VA and BB.
VA and BB act on like n copies of a Hilbert space. Are they able to mix those copies so they don't just?
Yeah, they are able.
Factorize.
They are allowed
Okay.
to do anything to.
And indeed, the one that ends up being the supremum, or that ends up saturating these, does it tend to do that? Does it tend to?
So yeah, so that's one of the key open question, whether you really need like whether this thing is superlinear, like does it before I divide by n, is it superlinear? And it's still an open question. For all the examples we know it's linear, which means you don't really need that coupling. We don't know a case where this coupling really gives you an advantage, but in general, we don't know.
Okay, thank you.
Thanks.
I was wondering, do you have a computable version of this without the optimization, or some other quantity that bounds it? Or maybe you'll talk about it, I guess.
So for some cases, we know what a VA give you the best choice. So there are cases where we know, yeah, but not generally. In general, we don't have a computable version. I mean, well, yeah, there are two things. Right? One is the optimization of VA. One is this n dependence. So if we could certainly define J1, which is just one copy, and then there is this. That's still a very useful quantity, as we will see later. It will bound the correlation functions. But even that, there is this optimization of VA. But for many cases we check, actually, you can choose VA to be swapped, as we will show later. Okay, good. Okay, so let's first check. Now we will discuss some properties of this quantity. First, there are several simple properties. So if you have AB that are space-like separated, then this quantity will reduce to the ordinary mutual information. So what happens is that, let's say if you have a quantum circuit, so it's well defined to have space-time separation, right? So space-like separation. So I have A here and B here. Then the time evolution is useless because you can just undo it, right, without affecting what happened to B. So then basically AB is the same as at equal time. And then now I still need to discuss what is the VA here. And what happened is that you can just take a VA to be swapped. You just take A out, and then W is your A. So rho BW is just the same as your rho AB. And you can show that's the optimal thing you can do, because a VA here followed by tracing over A can only reduce relative entropy, right? So if you have rho BW already have the same relative entropy as rho AB, then it's already the optimal choice. But you see, you cannot do that if B is time-like separated with A, because you need to worry about, like, you cannot trace over the time evolution here. Right? Okay, and then another important property is this quantity is the same as the ordinary mutual information. It's monotonous under quantum channels. If you have a state like this, and you say, before I feed it into my experiment, I first apply a quantum channel on A. And then you can show that can only reduce this quantity. Why? Because that's like, because you can just think that the whole thing as your VA prime. But I can always take a dilation of the channel, and then it becomes an isometry. Then I can combine it with whatever VA you choose in your experiment, and you call that VA prime. So that will be, so it's like you are doing the same experiment, but now you have some restrictions on the VA prime because it must have this part. So it can only reduce your supreme, right? So that's why it's monotonous in NA. It's also monotonous in NB, which is just directly follows from the property of relative entropy, because we have relative entropy of rho BW, right, between 0 and 1. So it's monotonous. And then another property is that if you have this quantity equal to 0, then clearly by construction there is no connected correlation, because 0 means that the state is the same as the state where as the 0 case, right, where the two are totally uncorrelated. So that's clear. Like only product state can make it 0. there is a formula. We want another property is that you can decompose this the space-time mutual information into two terms. So the key thing is that there is a key difference between our case and the spatial case, which is the zero, the factorized state, is not the rho B cross rho W for that state. If it were rho B cross rho W for the same state here, then you just get the mutual information, right? You just get ordinary mutual information between the ancilla W and B. But that's not the only term, because the case zero drawn here on the left, case zero, when you measure B, what you see is a system that was untouched at A. Right? What you see is the original expectation value of operators of the original state without coupling with the ancilla. And in the case one, for state BW, even if you only look at rho B, even if you trace over W, you see the average effect of this measurement channel earlier, right? Of what you did earlier. Right? What you did this here will be a non-trivial quantum channel. It will have a non-trivial effect even if you don't look at the measurement result. That's the key difference between space-like separated and time-like separated. So that makes this, according to some chain rule of the relative entropy, you can write down this decomposition, that the space-time mutual information is a sum of mutual information in the one state. Like you couple your system with your ancilla, and then later you look at mutual information of your ancilla W with some other some regime B. That's a natural term here. But there is another term, which is the relative entropy between the influenced state B and the original state B. And that term is there, is telling you that even if I do the measurements in A and I just throw away, I don't look at the measurement result, it still have a non-trivial effect on B. And that's measured by that term. And that term is very important because it doesn't even have an upper bound, right? It's relative entropy could be diverging. And yeah, actually, like you can look at some examples of cases where you can design different cases where like the first term is zero, like the relative entropy term is zero, but there is a non-trivial mutual information, or you can look at a case where there is a non-trivial relative entropy, but trivial mutual information. I think I will skip the details here. So the other quantity, another property is we want to show that there is a bound of correlation function in the same way as ordinary mutual information. And in space-time, you need, because the operators in space-time, time-like separated regimes, they don't really commute with each other. So you need to look at different kind of correlation functions. We don't have to look at these two types, but these are natural choice, especially like the commutator between Heisenberg operators, that's like the response function. So we can show that our quantity, and you don't need to go to n copies, just one copy, take one copy and do this to our space-time mutual information, and that gives an upper bound of correlation functions. And the way to prove that is really constructive. It's just saying you are allowed to do any measurements in A, right? So I will just design something that measures that correlation function. So what you do is you only need an ancilla with 3 states. And then the 3 states, 0, 1, 2, and you say, depending on the state, if the state of the ancilla is 0, I will do nothing. If the state is 1, I will do my measurement. I will insert my operator OA. And then 2 is just inserted so that the whole thing is unitary. And I will never use 2. So then what happened is, maybe it's better to directly look at this picture. What happened is that you could introduce that basically control the measurement here. So what you're doing is you're measuring, you are applying identity. If you have xa equals to identity, then this state of the W will remember that, so A equals to 0. And then if the state is 1, you will get an operator, you insert an operator OA here. Right? So then you get this quantum superposition, you get this entangled state of your ancilla and the system. And then later, by measuring different operator here on W, I could extract different correlation functions, different kind of childish correlation functions in the original system. For example, if I make that poly Y operator between 0 and 1, what happened is it must be 0 here, 1 here, or the other way. So what you measure is a commutator. It's OA here or OA there, and with a minus sign. And if you put a poly X, you are measuring the anti-commutator. And so in this way, and then you can show that that so J1, because it's optimized over choice of VA, so it should be bigger or equal to the relative entropy for this particular choice. And the relative entropy for this particular choice gives you upper bound of correlation functions, because you can show that the expectation value of this kind of equal time correlator for the ancilla exactly reduced to the correlation function you want. Yeah, and then when you go back to look at these formulas, the anti-commutator one is the one that reduced to the ordinary formula when you have space-like separate regions. The other one just becomes 0 if it's space-like separated. Any questions? Okay. I should. Yeah. So the other thing is, I should mention. So there is this causal influence which can also be bounded by this space-time mutual information, and that's just some other way to probe the system is you insert a unitary at A, and then see if that affects the state at B. And the reason why we propose that in this earlier work is that that's something that's 0 if you have a you have space-like separation. Like if you do general measurements in A, there could be non-trivial correlation with B even if they are space-like separated. But if you have unitary in A, it has trivial influence on B if they are not time-like separated. So anyway, so that's because that's just another way of probing the system. So it should also be bounded by our quantity here. And then one other property is that this space-time mutual information, because we showed earlier that it's monotonous. It's monotonous under quantum channels. So as a special case of quantum channel, you can think about partial trace, which means that the relative space-time mutual information between A and BC will be bigger or equal to that between A and B, because going from BC to B is just taking partial trace. So okay, so that difference is defined in the ordinary case is defined as conditional mutual information, and so that's also just strong subadditivity. So that quantity here, so we could ask whether it has similar property here as the ordinary case. So indeed, what we can show is a similar Markovian condition as the ordinary mutual information case. Like if there is a region ABC such that JAB is the same as JABC, so this difference is 0. If this difference is 0, what that implies is that all the correlation, there is non-trivial correlation. In general, there could be non-trivial correlation between A and C, but they are actually all mediated by B. Like there is correlation between A and C, but it actually is just, what actually correlates with A is just B. And then because A, B, and C are correlated, so there's some correlation mediated that way. And the more precise way to say that is the state of rho BCW can be reconstructed from the state of BW by Pat's map. And it's not so immediate, because you need to show that I can choose the same VA, like we are optimizing, so we can choose the same VA for the two sides of the equation. And turns out that's true. And then once you choose the same VA, you can just use the fact that the relative entropy is the same to do the reconstruction. And one interesting thing is if you do the Pat's map, you see that the reconstruction actually only uses the rho BC0, because it only uses the sigma state. So it's like if I know how much correlation there are already before I do the measurement between BC, then I can use that knowledge to construct all correlation functions involving ABC from that on A and B. So more physically, it's like if you have any Cavendish contoured correlation function, like from A and some operator on BC, oh sorry, this circle should cover both lines, but some operator acting on both B and C, you can always find another operator that only acts on B, so that the Cavendish contoured correlation function is the same. Like whatever I measure on BC, I can predict their result from just measuring B, if there is this 0 conditional mutual information. Okay. So that's so then now let me okay, so far these are like totally general properties. And then coming back to one of the questions earlier, so like what are the cases where we know how to compute this? So one case is if we consider an initial state of A, which is pure, and it's not entangled, of course, it's pure, so it's not entangled with anything else. So if A is pure, then the problem simplifies because I'm allowed to apply any general unitary VA. So instead of saying VA, I can just say I have a state after you apply VA, which is arbitrary, right? Because the initial state is pure, I can apply VA and get anything. So then the problem becomes just a characterization of the quantum channel that takes A to B. So it's like I can feed any general state to the quantum channel, and then ask whether the output looks different from a replacer channel. Replacer channel just throw away your state and feed back the original feedback a fixed state, which was the rho B zero. So that problem has been studied. That's called a quantum channel discrimination problem. So it turns out that quantum channel discrimination for this particular kind of replacer channel is known to be linear. So in that case, we can use their result and we can use their proof that tells us that our Jn actually doesn't depend on n. Like you don't need to go to more than one copies. And for more general channels, if it's not a replacer, that's actually not true. Okay, so that's one case we know. So it's pure state, initial state for A. And then we can go a little bit more than that. If the initial state is not pure, but it's not entangled with the rest of the system. Like maybe it's entangled with some bus, but the initial state of my system is just the initial state of A times the complement of the system. If it has that form, then we can show that the swap, like we can always choose VA to be a swap operator, and that is a saddle point. Like we can show locally it is it satisfies this supreme condition, like to the first order. And we don't have a proof that that's the leading saddle point, but all our numerics shows it's the leading saddle point. And in that case, you can write down explicit formula for this quantity. Like if you know this is VA, then the only thing left that you optimize is your initial state of W, and you can do that. And then so you can see, for example, for a single qubit, you can see some numerically some how big is that relative entropy. I think I'm more than 30 minutes. Yeah. Okay. Now I will in the last few slides I just show some examples. But maybe I should ask if there are questions about these properties here. Yeah. Okay, if not, let me discuss some examples. Yeah, so just to get some more physical intuition. So first, what happens if U is a higher random? And so if A and B are small subsystems, and then we are thinking of a dynamics that's a higher random, then of course the state of B will be independent from the state of A. It will always be maximally mixed. So that will be a trivial case where the JAB is 0. But if you think about a thermal system where you have thermalization, but there is an energy conservation, then the state of B is not entirely independent from A, because it remembers energy. And so I can take on the coupling VA, which put in energy to the system. That will be remembered for time later. So say if U is a time evolution for a long time, then energy is the only thing it remembers. So now if you look at JAB, it has these two terms. One term is the mutual information. And the mutual information basically is just telling you that there is a classical correlation between the energy you put in and the energy that shows up later. And because the energy will go to the whole system, so there is a reduction of like 1 over system size. But anyway, that's a small part because it's just a 1-bit message, right? One real number message. But the main leading part is the relative entropy, because the state at different temperature have a big difference, and there is a bigger relative entropy, which could be determined by the free energy of the thermal state. Yeah, so that's, and then we could do some more explicit study of this problem. For example, you can think of a Floquet system that's thermalized, and then you can see like, okay, as time goes on, this JAB quickly goes to 0 because there is no energy conservation. It's just like just like a hard random case. But on comparison, you can look at like an MBL system, where if you have a many-body localized Hamiltonian, and then you say you study the space-time mutual information between the same site A and itself later, then you see this J is close to like it. First, at short time it diverges because it's like you have a pure state to start, and then if you want to distinguish. If you want, it kind of have a perfect correlation with itself. So when you replace it by something else, you can just replace it with the orthogonal state. Then it diverges. It diverges logarithmically at short time. But what shows the MBL is that at long time this thing remains finite. And so when you have a long time, there's still a finite correlation between A and B. So you see that shows up as a saturation of this. JAB. Okay, so that's all what I plan to talk about. So in summary, we have this quantity that generalizes mutual information, and it has some properties similar to mutual information, like monotonicity and like the bounding correlation functions and the property, the Markovian property determined by 0 conditional mutual information, and so on. And then, of course, there are natural questions like can we show that in general whether it's linear or superlinear, and is there some relation with other measures like quantum channel capacity and other kind of quantum information measures of quantum channels, and then whether there are some other examples we can compute. Yeah. Thanks.
Yeah, thanks. I'm just curious, there's all this work on mappings of, entanglement measures and random circuits to stat-mech problems. Have you thought about what this would correspond to in that setting?
Yeah, we thought about that, and I think we did some calculations. Yeah, so you can, if you choose the VA, if you fix the choice of VA, for example, I can choose it to be swap, then you can map this, for example, mutual information, it becomes some spin correlation. And the relative entropy is a bit more tricky. We will need to consider overlap between different different circuits and Rayleigh versions of that. Yeah, so we don't have a clear, simple result there, but it's something that can be studied. Yeah. Mm-hmm.
Maybe it's a stupid question, but so if you have an initial infinite temperature state, is this related to entanglement properties of the evolution operator?
Yeah, yeah. So if you fix the initial state to be maximally mixed, then sure. Or if you, then this will become a property of the evolution operator. So in particular, like if you fix the initial state of A to be anything that's not entangled with the complement system, then there is a quantum channel defined from A to B, and then this quantity is a characterization of that quantum channel. So in this particular case of pure state, this becomes the discrimination of quantum channel, the quantum channel discrimination problem. But I don't. I think, well, for example, there are other connections, like if you choose VA to be swap, then the mutual information term, which is mutual information of W and B, is just this kind of mutual information we studied in quantum channels. And so you have a choice state. So what happens is if the initial state is pure, then that's optimal. The swap is optimal. And in the case where initial state is not pure, but it's product with a complement system, it's probably optimal. I mean, it's a saddle point, and all the numerics shows it's a leading saddle point, but we don't have a proof. Yeah.
It's actually kind of related to the last question. Have you thought about using these to diagnose like dynamical topology or things in like where it's like topology of the unitary, not the states?
Yeah, that's an interesting question. Yeah, I don't. I mean, if we haven't thought about that. If we take A and B to be small regions, probably it doesn't. But I would guess you need to choose B to be a topologically non-trivial region.
Yeah, maybe A could be like the boundary of the.
If you choose A and B both have some non-trivial topology, like ribbon-like regions, that probably is an interesting thing we can study. Yeah. Thanks. Yeah.
So is this space-time mutual information asymmetric under exchange of A and B, and can it be used to probe like causality?
I don't know what the exchange means, because like they are, well, if you give me A and B, I know how to define them. Mm-hmm. But there is a time ordering which already. But so I would say, yeah, okay, maybe yeah, actually maybe it's good to comment. So if we use this general definition, like here, like I'm allowed to couple to these two parts, and then I can couple them arbitrarily with VA and VB, and then just optimize the relative entropy. I think you can see that its definition is symmetric. So if I don't even know their time ordering, then I can just use that general definition.
But if I don't have a direction of time, like my circuits I may make some measurement in the end such that change my time order. And
well, I'm assuming there's no hidden. Yeah, it's true. Like all these things are assuming like after I did this, we just trace over the system. Yeah, if you have a post selection, then certainly it will be all different.
Okay.
Okay.
You mentioned the Markovianity of the space-time conditional mutual information when it's 0. So for the ordinary conditional mutual information, there's also a bound that, it's lower bounded by some ability to reconstruct the state when you act on some fraction of the system. Is there something similar for the space-time conditional mutual information? Maybe I missed this, but.
I would guess so. I mean, to be honest, this conditional space-time mutual information was what we only thought about in the past few days. So we haven't gone there, but because we are using the path map in the same way as the ordinary case, like once we can show that this equation. Oh, okay. So I think one subtlety is if this quantity is not 0, then it's possible that the optimal choice of VA is different in these two cases. And that's the only difference from the ordinary case, which may make the argument a little harder. But if we take the same VA, then everything follows in the same way as before. So you will have an approximate reconstruction map.
Thanks.
And by the way, the reason why we can take VA to be the same when this is 0 is that if you choose the optimal VA for JAB, then the same VA must be optimal here, because if it's not optimal, then that means if you choose the same VA, then this is smaller than that, but that's not possible. Okay, yeah.
So regarding your open question that you mentioned, whether or not having more than one copy changes JN, so I'm kind of confused about how. I mean, there's some recent result. I think you also, in your quant paper, you also mentioned this. When there's more than 2 copies, you can do something. You can reveal exponentially more information. So why does that not provide an example where you can prove the separation between J2 and J1, for example?
Yeah, that's a good question. I think that's because we also, that was initially what we feel like, okay, maybe there are obvious examples where this is superlinear. Because when I have 2 copies, I could do swap measurements, which as in our qual paper with Dorita Aharonov and Jordan Kozler, we show that that's very hard to do using classical measurements if you do 1 by 1. But here, I think it's because we have this unrestricted coupling with the ancilla. Like, okay, so maybe the better way to say is because we are calculating the relative entropy. So relative entropy, let's say if I do this for one copy, and then I calculate the relative entropy between these two cases. And that relative entropy, if you think about this hypothesis testing interpretation, it kind of already take into the relative entropy is already measuring what you will classically, what you can do classically if you have many copies of the system. So that's not exactly answering the question, because that's saying like if you take many copies and then do arbitrary things in B, it will not make you better. So it doesn't say things about VA. I think roughly speaking, it's like if I'm, instead of asking about relative entropy, if I say I do a classical measurement here, and I'm only allowed to look at the measurement, the classical measurement output, then one copy and two copy will be very different. But here, because we are talking about relative entropy, the output state, which is a quantum state, so somehow that's the difference. Yeah.
So, sorry.
Hello. So maybe it is a silly question, but then say that in the case that when you have the dual unitary circuit, would you have some relation between the yo-yo kinds of mutual information and this space-time mutual information?
Yeah, my first comment is I think for dual unitary, probably as when the time separation is long compared to the size of the region, it will become 0. Like I think just you can show like at least the mutual information part is 0. We haven't thought more carefully about that, but my understanding is actually if it's a dual unitary circuit, then the correlation functions will all vanish. Yeah. If it's space-like, then yeah. If it's light-like, not. Yeah, and I don't think there is a direct relation between this one and if you tilt it. And well, first of all, that's not so well defined if the region is bigger than one side. But if I look at pair of sides, then yeah, you could look at this way as time or that way as time. But still, they won't be directly related because the boundary condition is quite different. Yeah, but I think that's an interesting question.
Okay, I think at this point, if there are any questions, we can postpone them for later. So thanks again for a very nice talk.
Thank you.